Welcome back to an Introduction to Real Analysis. We continue now with Chapter 3, Section 3, Important Theorems Regarding Continuous Functions. The theorems presented in this section contain possibly the two core theorems that make up an introduction to analysis: the extreme value theorem and the intermediate value theorems. Both functions hold in different formulations in general context, not just specifically for the version we're going to present. But these theorems for functions of a single real variable with the definition we've been using of a continuous function are, in a very concrete sense, the first real introduction to analysis as a big umbrella topic that most students encounter. So we begin with the following lemma: a continuous function mapping specifically an interval of the form a to b including both endpoints to the reals is bounded. Weierstrass theorem, which we will end up citing. What we're going to establish is that the range in absolute value is bounded above. This shows that the range is bounded. So for every point in the domain, x, the absolute value of the corresponding point in the range, f of x, is less than or equal to some constant m. This is what we want to establish. Let's assume to the contrary that for any choice of a constant, for example, 1, 2, 3, and so forth, there exists a point in the domain where this fails. So there is an x1 in the domain where the absolute value of f of x1 is bigger than 1. There is an x2 in the domain where the value f of x2 in absolute value is at least 2. There's an x3 in the domain so that the absolute value of f of x3 is at least 3, and so forth. Definitely, this sequence of absolute values is going to infinity. The first is at least 1, the second is at least 2, the third is at least 3, and so forth. But look at the sequence in the domain. X sub n is in between a and b. It's bounded below by a and bounded above by b. By Bolzano-Weierstrass, there is therefore a subsequence converging to some point, and this point must also be in between a and b. But our original sequence in the range was going to infinity. So this subsequence in the range is still going to infinity. However, back in the domain, we were converging to a point c, and the function was assumed to be continuous at every point in the interval, including the endpoints. C is such a point, so f must be continuous at c. Now we have a subsequence converging to c in the domain, where the function is continuous. Therefore, this sequence f of x and k in the range must be converging to f of c. However, we've already established that that sequence in absolute value is going to infinity. It is therefore not converging to the absolute value of f of c. So, a fairly straightforward theorem, but let's talk about it a little bit. There were two key steps that are important to point out. The domain is bounded. Because we drew a sequence of points in the domain, this allowed us to call on Bolzano-Weierstrass. It's important that the domain is bounded. Without this assumption, the theorem is false. F of x equals x is continuous on the entire real number line and definitely not bounded. So we definitely want the domain to be bounded, but we also need to include the endpoints. At a certain step, we had xn belonged to the domain, therefore we went to Bolzano-Weierstrass, and then we said the limit of the subsequence Bolzano-Weierstrass gives us is also in between a and b. However, if the domain didn't include a and b, the sequence converging to a point might actually converge to such an endpoint. So continuity at the point the sequence in the domain is converging to was crucial. Therefore, we need continuity including the endpoints of the interval. And a counterexample is 1 over x. This is continuous on the interval from 0 to 1, not including 0, but it's definitely unbounded as you approach 0. Recall also the definition of an absolute minimum. This isn't necessarily a calculus-specific definition, but most students saw it in a calculus course. An absolute minimum at a point c means that every f of x is bigger than or equal to that specific f of c. Similarly, an absolute maximum means every f of x is less than or equal to a specific f of c. If such a point exists in the domain, we say f achieves an absolute minimum or an absolute maximum, and we call such a value the absolute minimum or absolute maximum. Now, if S is a closed and bounded interval, then a continuous f is not just bounded, it must achieve an absolute minimum and maximum. Let's establish that. This is called the extreme value theorem. Suppose you have a function which is continuous, and the domain here is very specifically an interval including both endpoints again. It must achieve both an absolute minimum and an absolute maximum. Let's get to proving. Now, we just showed in the previous lemma that a continuous function whose domain is of this form has to be bounded. So let's let alpha and beta be the inf and sup of the range. Because alpha and beta are the inf and sup of the range, there are points in the range arbitrarily close to them, perhaps equal to them. That's kind of what we hope, that they're actually a min and a max. But specifically, for every positive integer, there are points back in the domain where the corresponding points in the range are arbitrarily close to the inf and sup respectively of the range. So we are finding points in the domain belonging to this bounded interval where the corresponding points in the range are getting very, very close to the inf or very, very close to the sup respectively. Applying the squeeze law to these inequalities gives us that f of xn must be converging to alpha and f of yn must be converging to beta. Now the sequences xn and yn are simply back in the domain, the interval from a to b, but that's a bounded interval. So by Bolzano-Weierstrass, we may pass to a subsequence of each converging to some other point. These points where the subsequence xnk and ymk are converging to have to also belong to this interval. Again, perhaps including the endpoint, which is why it's important that we have included them. But notably, they must be converging to a point where f is continuous. So f of xn is converging to alpha, therefore the subsequence f of xnk is converging to alpha. Since xnk is converging to a point where the function is continuous, f of xnk has to be converging to f of c sub min. Therefore alpha equals f of c sub min, and similarly beta equals f of c sub max. We're therefore done. The inf of the range is actually a point in the range. It is equal to f of something. And the sup of the range is equal to f of something, so it's actually a max. Let's take a look at the following example. X squared plus 1 on the interval from -1 to 2, including its endpoints. It has a minimum at f of 0 equals 1 and a maximum at f of 2 equals 5. You can simply look at the function and see what it's doing. But the domain matters a whole lot. On the interval from 1 to 5, a different interval, the minimum is at f of 1 and the maximum is at f of 5. If you change what interval you're looking at, of course the minimum and maximum can occur. Specifically, this maximum of f of 2 equals 5 is inside the domain of the next interval we looked at, but it's not where the maximum occurs. Okay, we'll take a look at more examples to show how these hypotheses matter very much. For example, consider f of x equals x. It's defined on all of the real number line and is continuous, but it definitely doesn't have a maximum or a minimum, which does not violate the conditions of the extreme value theorem because the domain is not stated as an interval including its endpoints. We really need a bounded interval for that to work out in the statement of the theorem. Another example, 1 over x on the interval from 0 to 1 is continuous on that entire interval, but definitely doesn't have a maximum. It also does not have a minimum. The function is not even bounded above on the interval. So the inf of the values taken is 1, but that's not actually f of anything in this interval. The infimum of the range is 1, which occurs at f of 1, but we've specifically cut that point out of the domain. So it is quite important that we are including the endpoints. Another example, take a look at the following function. It's 1 over x, again on the interval from 0 to 1, but we're going to give it a value that f of 0 equals 0. It's now defined on a closed, bounded interval, but it still does not have a maximum, because it's definitely not continuous on that entire interval. So all of the hypotheses of the extreme value theorem are necessary. The function has to be continuous, the interval has to be bounded, and the interval has to be closed. So all conditions definitely necessary. Now, the proper formulation in a broader analysis sense is that the extreme value theorem holds for any function that is continuous on a bounded closed set, or more generally a compact set, Now, the technical definition of what makes a set compact is something that we're semi-intentionally avoiding. It's possible to avoid working with compact sets when you're restricting yourself to analysis on a single real variable. If you start trying to apply these definitions to more general contexts, you really want to talk about compact sets. So we're not getting into compactness. The good news is that in the real number line, or in Rn more generally with standard topology, another term we're not going to get into, compactness of a set is equivalent to it being closed and bounded. Now, a closed bounded set in the real number line does not actually have to be an interval including its endpoints. It could, for example, be two disjoint intervals including all of those endpoints, or maybe just a single point that is a closed bounded set. So the notion is equivalent. We're just presenting a semi-simplified version of it because, again, this is supposed to be your sort of first foray into analysis. Moving on to the other important theorem from this section, the intermediate value theorem. So this is also one of the cornerstones of analysis. Usually one comes across this just called the intermediate value theorem. Much less common is to see it called Bolzano's theorem. In general, I'm just going to abbreviate it as IVT. I've always seen it referred to just as the intermediate value theorem. Not to sell Bolzano short, Bolzano's theorem I would tend to think of as the Bolzano-Weierstrass theorem. So to prove the intermediate value theorem, we're going to start with a simpler lemma, just like we started the extreme value theorem with another simple statement. Remember, we first started by saying a continuous function on a closed bounded interval is bounded, and then we showed that it had a max and a min. So let's start off with that lemma. We again have a function continuous on a closed bounded interval. Now let's assume that f of a is negative and f of b is positive. Then there is an intermediate point, some point in between a and b, where f of c is 0. So if a continuous function goes from negative to positive, it had to actually be equal to 0 somewhere. Let's start the proof. We're going to define two sequences an and bn. These sequences are going to have a few properties. First of all, we want to be pulling points out of the domain. an and bn will always belong to the interval from a to b. An is chosen so that the corresponding points in the range f of an always less than or equal to 0, whereas f of bn always positive. Also, the sequences an and bn are going to be converging to something. An is going to converge to something that we're going to call capital A, and bn is going to be converging, and we're going to call its limit capital B. Also, we're going to show that the distance between an and bn converges to 0. Once we put all these pieces together, we will conclude that f of a must equal f of b must equal 0. Because we are continuous in here, if an is converging to a, f of an must be converging to f of a. But all the f of an's are less than or equal to 0, so we conclude f of a is less than or equal to 0. Similarly, we will get f of b is bigger than or equal to 0. And since the distance between an and bn is converging to 0, we'll get that a equals b. That's the broad outline. We'll go over it in detail. So let's stick these desired results over on the right here. So that little box there is what we want to establish. So we're going to begin just by picking a1 and b1 to be the left and right endpoints of our domain. Now let's inductively assume we've chosen a bunch of points that satisfy essentially everything we need. First of all, that the a's are increasing, the b's are decreasing, but they bound each other. We also want f of an to always be non-positive and f of bn to be positive. So if we have done this, if f of the midpoint is less than or equal to 0, pick that as your next an plus 1. If, however, f of the midpoint is positive, pick that to be your next bn plus 1. Note that you always keep one of your a's or b's equal to the one before it. If f of the midpoint is non-positive, make that your next a, and keep the right endpoint as your next b. If f of the midpoint is positive, keep the left endpoint as your next a, but make that midpoint your next b. So no matter what, you're making the midpoint one of the points that you pick for your sequence and keeping one of the endpoints the same. And you are specifically making the choice in a way to maintain that f of the a's is always less than or equal to 0, and f of the b's is always positive. So if you have a sequence of a's and b's that has all of the properties we started with, your next choice will do the same. We're specifically fixing one of these two to remain unchanged while making the next point chosen to be a midpoint of the two. So this increasing a's versus decreasing b's and never crossing each other will be carried through. And how do we pick whether we keep the a the same or keep the b the same? In order to very specifically maintain these inequalities along our sequences. So what do we have? We have a sequence an and bn, where the an's are monotone increasing, the bn's are monotone decreasing. Also, f of an is never positive, but f of bn is always positive. The two sequences are bounded, they bound each other, and they're monotone, so they have limits. So the an's are converging to something, the bn's are converging to something, and the things they're converging to are in our interval of continuity. However, the distance between two consecutive ABs is 1/2 of what was before, because we're always picking the midpoint of the interval between the previous A and B. So by keeping one endpoint the same and jumping to a midpoint, you are cutting in half the distance between. So the distance between A and B goes down by a factor of 2 every time you increase the index. It follows then that the distance between them converges to 0, therefore capital A and capital B, their limit points, have to be equal to one another. Now, because f is continuous at A and an is converging to A and f of an is less than or equal to 0, we find that f of capital A is less than or equal to 0. But similarly, bn is converging to B where the function is continuous, but all of the f of bn's are positive, so f of b is bigger than or equal to 0. But since A equals B, we have f of this point less than or equal to 0, f of this point also bigger than or equal to 0, therefore f of capital A must equal f of capital B must actually equal 0. Here then is the full intermediate value theorem. Let f be a continuous function on a closed bounded interval. This is sort of a running hypothesis for all of the theorems here. Now you pick a value y, so that one of the following chains of inequalities holds. Essentially, if f of a is less than f of b, y is simply chosen to be in between them. But if f of a is bigger than f of b, again, y is chosen to be in between them. In general, y is an intermediate value between f of a and f of b. Then there has to be some point in between a and b that actually achieves that value y in the range. There is a c so that f of c equals y. Okay, so let's move on to the proof. Recall this lemma we just proved. If f of a is less than y is less than f of b, I'm going to define a new function g of x to simply be f of x minus this constant. In this case, all I have is a continuous function. The hypothesis was that f is continuous. I've subtracted a constant. Constant functions are continuous. The difference of continuous functions is continuous. So g is continuous, but because we have subtracted y, we get that g of a is negative and g of b is positive. So by the previous lemma, there is a point somewhere in between where g of c is equal to 0. How can g of c equal 0 exactly when f of c equals y? Similarly, if you begin with the other chain of inequalities, instead of taking f of x minus y, you take y minus f of x, but you'll end up in the same place. So the previous lemma really did all the heavy lifting for us. A comment now about what's called the bisection method. This went into how we proved the intermediate value theorem. So this suggests a fairly straightforward way to find solutions to f of x equals 0. Provided you have a continuous function on a closed bounded interval, and you know the function is changing from negative to positive or vice versa on that interval. Essentially, check the midpoint of the interval, then pass to a subinterval, either the left or right half, on which your original endpoint restrictions still hold. You keep applying this until you have an approximation to the root strong enough for your needs. So in general, instead of finding roots, you can find where f equals g by finding roots of f minus g. So this little trick applies for intersections of curves, not just roots of curves. For example, let's consider this polynomial x cubed minus 2x squared plus x minus 1. Observe that f of 1 is definitely negative. 1 minus 2 plus 1 minus 1 for a result of minus 1, but f of 2 is actually a positive number. This is a polynomial, so it's continuous everywhere, so it's definitely continuous from 1 to 2, including the endpoints, and it goes from negative to positive. So there is a root somewhere in between 1 and 2. So starting with that interval, negative on the left, positive on the right, by which I mean the range, negative on the left, positive on the right, compute the value at the midpoint, and then move to whichever half has the same negative to positive kind of change. And repeat until you have an approximation to the root good enough. So we begin by noting that f of 1 is negative, f of 2 is positive. The midpoint is 1.5, and 1.5, f of 1.5 is negative. This is simply a computational check. So the original went from negative to positive. The midpoint is negative, so going from 1.5 to 2 will maintain the same negative to positive change in the range. So 1.5 to 2 now becomes our domain. Compute f of its midpoint, still negative. So to maintain this negative to positive motion, make your new domain 1.75 to 2. Computing at its midpoint, you get a positive number. So 1.75 to 1.875 now has that negative to positive change. Compute f at the midpoint here, positive. So now you keep your negative endpoint here and take your new positive endpoint, and you just keep doing this over and over again. So notice that we now have narrowed it down to the root being between 1.75 and 1.8125 specifically. Therefore, whatever the root is, if we round it to a single decimal point, it will round to 1.8. So we can conclude, if all we need is a single decimal point of accuracy, that a root of this function is given by 1.8. Okay, and in fact, it's 1.7549. This is just throwing it into a computer and asking. But you could just keep iterating this process until you narrow down your domain to be as small as necessary to make a sufficient claim for accuracy on the root that you found. This is the simplest method to find roots of polynomials, and finding roots of polynomials is a very common problem that shows up. Now, in general, finding roots to functions is actually quite difficult to do quickly, precisely, and automatically. There are, in fact, better ways of doing it for polynomials. Newton's method is the one that comes to mind. But one advantage of this bisection method is that it is extremely simple. It's just check, move to a new interval, check the midpoint, move to a new interval, check the midpoint, and you just keep doing that. So the moment you find an interval where the intermediate value theorem applies, you can just keep doing this, and you can now find a root up to whatever precision you needed, and you will get there in finitely many steps because you're always cutting the width of your interval in half. Furthermore, the bisection method will work on any continuous function, not just a polynomial. Newton's method will come up later. It involves taking derivatives and using tangent lines, and there are specific scenarios where Newton's method goes wildly awry and just fails to work. This bisection method will always cut in half the interval at every step. It's just usually an inefficient way to do it, but it always applies. Okay, the intermediate value theorem guarantees that we can always find at least one point in the domain where the range is our target value in between the values at the endpoints. But there can be more than one place where this value is achieved. If we follow the procedure of the proof, you can find approximations to one such solution. If we want to find others, that takes more work. Polynomials of even degree, for example, might not have any real roots. There's no real number where x squared plus 1 is equal to 0. Odd degree polynomials always have at least one real root. So suppose you have a polynomial where the leading coefficient isn't 0 and it is an odd degree polynomial. Then there is at least one real root. We begin the proof. So suppose you have such a polynomial. Note that f of x is equal to 0 if and only if dividing by the leading coefficient is still a root, because we have assumed that this leading coefficient is not 0. So without loss of generality, we're just going to pass to a monic polynomial, a polynomial of odd degree where the leading coefficient is 1. We haven't changed any of our results, and this is just going to be a bit of a convenience. Okay, the coefficients of this new polynomial are just the coefficients of the previous one divided by the leading coefficient. Let's take a look at this monic polynomial. Okay, let's understand this chain here. The first equality is quite straightforward. G of x minus x to the d is just all of these other terms. Now inside here, we're going to apply the triangle inequality across this finite sum. What terms do we generate? An absolute value of a b times an absolute value of x, where we have canceled out this x to the d down in the denominator. So we start with index 0, go up to index d minus 1. We always get the absolute value of the coefficient, and then an absolute value of x to subscript minus d. Note that I is going from 0 to d minus 1. So it is less than or equal to minus 1. When I equals d minus 1, that's the biggest that will ever be, minus 1. So as long as x is past the value of 1, if I take this positive x and I raise it to a significantly negative power, that's less than or equal to just raising it to the minus 1 power. So now, all of this less than or equal to this sum. Every single one of these absolute value of x's to a power less than or equal to a constant 1 over x, which you then factor out. Defining capital M to be this sum of absolute values of bi's, we get this inequality right here. Provided x is at least as large as 1, we have this inequality, where m is a fixed constant. So now take a limit as x goes to infinity. M is a fixed constant, and we are now dividing by x and letting x go to infinity. So this absolute value has limit 0. So it is eventually less than 1. I'm not so concerned with its limit being 0. What's useful is that past a certain value of x, it is definitely small. How small? We're just going to say less than 1. If this is less than 1 in absolute value, then this without the absolute value is in between plus or minus 1. Multiply the x to the d. Since x is going to infinity, x to the d is positive, so I don't need to flip inequalities. Okay, so now we see that x to the d minus g of x is in between plus or minus x to the d. On the right-hand side, since x to the d minus g is less than x to the d, I actually subtracted a positive quantity. So past a certain value of x, g of x must be positive. If you do all of the same steps but look at g of negative x, you sort of go through the same rigmarole, and you end up with a claim that to the left of a certain value, g must be negative. Okay, and I'm really skipping over the details here, but if you've done one half of it, the other half is not so surprising. So now what have we found? Some interval where g is continuous because it is a polynomial. It's negative and positive on the endpoints. So what do we conclude? Thanks to the intermediate value theorem, there is a root somewhere in between, and that now back applies to the polynomial we started with by remultiplying by the leading coefficient a sub d. Way back when in chapter 1, we showed that the square root of 2 is a real number. It was actually fairly difficult, but it was done just through sup and inf of sets existing through the completeness axiom. Now, however, with the intermediate value theorem, we can quite quickly show that for any positive c and any positive integer k, there is a kth root of c. Consider the following expression. Since k is a positive integer and c is a constant, this is a polynomial, so this is a continuous function on the entire real number line. As a very special case, if c is 1, then x equals 1 is a root. We want to find a root of this expression that will exactly be a solution to x is the kth root of c. In other words, every root of 1 is equal to 1. Not a big surprise, but at least true. So let's suppose c is not 1. Observe that f of 0 is definitely negative. Remember, c is a positive constant. So 0 to the k minus c, definitely negative. If c is less than 1, then f of 1 is 1 minus c, since c was less than 1, f of 1 is positive. However, if c is bigger than 1, you can similarly compute that f of c is c to the k minus c, factor out a c. Since c was larger than 1, this is positive, and c was assumed to be positive, so now f of c is positive. Either way, you have an interval where your function goes from negative to positive. In the event that c was less than 1, that interval is just 0 to 1. When c was bigger than 1, that interval is 0 to c. However, we have a polynomial, which is continuous, changing from negative to positive. Therefore, it has a root. And again, a root of this polynomial corresponds to a kth root of c. So what have we shown? Every positive number has a kth root, where k is any positive integer. Here's another example. It's totally possible to find functions where the conclusion of the intermediate value theorem holds, even though the function isn't continuous. Take a look at the following. It's the sine of 1 over x, which clearly doesn't exist when x is 0, so simply fill in that value and say that f of 0 equals 0. This function is discontinuous at x equals 0, but if you pick any interval in the real numbers, f of a and f of b exist, pick any y in between them, it is totally doable to find a point in your restricted domain where f of c is equal to y. We're leaving out details because this is an exercise. Okay, but this function is not continuous, but still satisfies the conclusion of the intermediate value theorem. So the intermediate value theorem says that if you have a function continuous on a domain which is a closed bounded interval, the range contains every value between the values at the endpoints. But the extreme value theorem actually says there's a maximum and minimum value in the range. So if you look at the restricted domain between where the maximum and minimum are achieved, in whichever order makes sense to write down the interval, f of x must actually now achieve all values between its absolute max and absolute min. This leads to the following corollary. If f is a continuous function whose domain is a closed bounded interval, then the range is either a single point, if f is a constant, or the range itself is another closed bounded interval containing both its endpoints, if f is not a constant. So the general formulation of this corollary is to say that if f is continuous, the image of a compact set is another compact set. You feed in a closed bounded interval, you get out a closed bounded interval or a single point. Depending on terminology, you may or may not consider a single point to be a closed bounded interval. So again, we are kind of avoiding talking about compactness. But if you're familiar with the notion of compactness, that's kind of really what this corollary says. Let's go over what we talked about. The extreme and intermediate value theorems are big tentpole theorems. In the study of analysis, these are just like big flags that get waved around. You have reached an important theorem. Now, our presentation has specifically avoided using the word compact. The formal definition of what makes a set compact is a little intimidating at first. So as a first sort of introduction to analysis, it is reasonable to avoid it. However, if you are going to study further, or maybe if you're reviewing this after previously seeing the notion of compact sets, try to draw those connections.